Yeah. Hello, everyone. Thanks for coming. It's my great pleasure to welcome Titus Barek, who is finishing up his PhD at North Carolina State University. So Titus is interested in HCI as well as software engineering. He also has a great deal of industrial experience, including being a research scientist at ABB, and he was also an intern at Google and at Microsoft. So welcome back, and looking forward to your talk.
Okay, thanks a lot. So can everyone hear me okay? Yeah. All right, good. So my name is Titus Barek. Thanks again for the introduction. Good morning, everyone. So I assume it says I'm a student at NC State University, wrapping up. And in the past, I've worked at Google as a software engineering intern a few summers. The first time I worked on Google Web Server, which is the website that powers google.com. I also worked for a group called Machine Intelligence at Google, and this is different from machine learning. The machine learning people, they take data and run all sorts of algorithms and do statistics, and the machine intelligence group is a group of individuals who make tools to help support machine learning experts. So that's a little bit about my background. Today I'm going to talk a little bit about the stuff I've done in industry, and also a lot of my research work on what program analysis output is, why that's important, and why that's something worth studying and improving for software engineers and data scientists. So before I dive into the details, I'd like to just set the context sort of for my research approach and research philosophy. So the work that I do, I think of as sort of being in the intersection of HCI and software engineering. And I've put an example here of a person pulling a heavy object through the use of a pulley. And that's sort of how I see myself as a researcher, in that I don't think of computation as replacing people, but I think of computation as tools that can help people perform tasks more efficiently, sort of like the pulley. And in some cases, enable them to do tasks they might not be able to do otherwise. So maybe this person could lift this heavy object, but having a pulley makes their life a lot easier. And so I think of my research in several ways. First, I try to understand the tasks that the person is trying to do, right? Oh, it looks like they're trying to lift this heavy object. And then I investigate prototypes and tools to see if I can help improve their situation and make their life better in some way. And then I follow that up by evaluating that tool to see if it actually had the impact I thought they would, maybe by surveys or user studies, to see if the task time was shortened, they were more effective at the task, and so on and so forth. And that's sort of how I apply my lens of research to all of the studies I'm going to show you today through different facets. So I talked a bit about my research philosophy at a high level. My primary sort of thesis interest is in this idea of an area known as programmer comprehension, which is how people go about sort of working with programs, understanding programs, and that sort of thing. In particular, I'm interested in this idea, this cognitive process called self-explanation. And intuitively, you can think of it this way. So when you're trying to fix a bug, you verbalize and say things to yourself in order to solve the problem. And what you're doing there is called the self-explanation activity. And this happens in a variety of different problem-solving tasks. So I'm going to look at this in sort of three ways. A tool, such as a compiler, gives you some sort of a message, and this person has made a bug report and said this error message is very confusing. So that's sort of a linear explanation style. The computer initiates a message, gives you some feedback, and it's up to you to self-explain what's wrong. More recently, I've been interested in this idea of transactional explanations. So instead of being this one-way conversation where the computer says something to you, it's a mixed sort of initiative interaction where the human and the computer work together to solve a problem. This particular example, it's hard to see, but there's a catch exception defect in exception handling, and working with the computer, the person is dragging and dropping where they want the exceptions to go, whether they want to throw them or catch them, etc. There's a third form of explanation that I've sort of been thinking about working with folks at Microsoft Research, which is it's not a computer-initiated explanation, but it's user-initiated. So I have some data maybe, and I want to ask questions about that data and have an explanation for why a system is behaving a certain way, why maybe a log file is looking the way it is, that sort of thing. So these are not computer-initiated messages, but I need tooling to be able to ask questions and get explanations about some sort of data that I'm looking at. Okay. Most of my research to date has focused on integrated development environments, or IDEs, mainly because that's the dominant paradigm under which software developers program. So hopefully, maybe all of you are familiar with IDEs, but if you're not, I'm particularly interested in the idea of anomalies or errors that happen within the IDE. So we talked about how computation gives you feedback. And so the compiler or the IDE gives you feedback in several ways. So it gives you an error message down here below, similar to how consoles do. But it also uses a variety of other textual and visual affordances. So you can see there's the red squiggly lines, sort of to help you understand where the problem in your code is. There's tooltips, right? There's even what we call like ambient affordances, things you can see on the side. So I'm not allowed to move very far, but like the scroll bar, you can see there's little red markers, so you can, in your periphery, sort of see notifications or problems in your code. Okay, so these are all sorts of explanations the compiler is giving you through various messages and visual indicators about things that are wrong in your code, and it's up to you to self-explain, to continue that process to resolve whatever the defect is. Visual Studio is sort of representative of other IDEs, so IntelliJ, very similar sort of idea, tooltips, console bar, etc. So obviously these sort of affordances are there to help developers understand what the problem is and resolve problems quickly. So what's the problem? Well, the problem is that program analysis tools today don't have the best reputation for being human-friendly to developers in terms of how they give their output and how they present their explanations for a problem. So if we look at the literature, we see that these tools have been described as appalling, difficult to understand, not very helpful, misleading, and sometimes unnatural. And so these are the more polite expressions that I found in the literature about the types of feedback their tools are giving them. So we might say, well, fine, the output's sort of confusing, but you know, if they're expert software developers, they figure this stuff out. This is only a problem for novices. But it turns out that that's not the case either. It's not just a problem for novices. For example, Google conducted a study on compiler error messages, and they found that over a quarter of their builds were failing due to compiler errors that developers were introducing into their code. And what's worse than that is there was a very high median resolution time for fixing these defects, which suggested that it wasn't really immediately apparent to them what they needed to do based on the error to fix the problem. So what's the practical impact of this for people who are using tools? Well, as you know, the first study identified by, this is Christakis and Chris Bird here at MSR, there's a lack of adoption of the tool. If people don't get program analysis output that helps them, they tend not to use the tool, or they ignore the output of the tool, or they use something else. And this is particularly frustrating in software engineering because as developers, we write very sophisticated algorithms, come up with very nice program analysis techniques, and sort of at the very last mile, when we're about to present something to the user, that's when the system's breaking. So that's really unfortunate when that happens, because they could significantly benefit from these tools. The other problem is that poor notifications reduce developer productivity. They spend significant amounts of time trying to understand the situation and then resolving a particular defect, as we saw in the Google study. And the worst part of this is it ends up leading to defective and buggy programs. So if there are mismatches between how the compiler or the IDE has given them information versus the questions the developer is trying to ask from the tool output, it can lead to not only incorrect fixes, but incorrect judgments about the problem. So they may think they've correctly solved the defect, but they've really just misunderstood what the output was saying, and they end up applying an incorrect fix or an incorrect resolution of some form. Okay, so that's sort of the setup for this, and I'm going to look at this through 3 different studies that I've done in the past at different resolutions. So the first one I'm going to look at in some detail. This is an eye tracking study. The second one I'm just going to look at briefly. I'm going to ignore the sort of introduction methodology and talk about a tool that we've built that does interactive explanations for certain types of compiler error messages. And then I'm going to sort of broaden our scope from compiler sort of tools like IDEs and look at challenges people are having with more general sort of data science environments and how we can go about helping them. And then I'll end the talk with some directions and conclusions. So our first study, do developers read compiler error messages? This is a question that is actually towards several research questions toward understanding how developers use information in their IDE, specifically in the presence of an error. There are a lot of studies that look at how developers navigate code, how they write code, how they read code, but we're specifically interested in what happens in situations when they have an error present in their system. How do they react? What information do they use? How do they go about resolving their problem? So interestingly, the reason we had the title for this particular study is some researchers were speculating that maybe developers actually don't read the messages that we give them. So if we write really fancy static analysis tools and try to help the developer, the problem isn't that the error message is bad per se. It may be possible that there are other affordances that help them solve the problem where they don't need the message itself. So let's do an example. So I have a statement here, a switch statement, and I haven't given you the compiler error message, but maybe I just tell you the location of the error, right? I say, here's the problem on this line. Most of you, if you are programming in C# or Java or languages like that, you might conclude that, oh yeah, it's just missing a colon on the end, right? And you're able to fix the defect in the code. And if you looked at the error, you might see, well, yep, that's a syntax error on default, add a colon after the token. So maybe there's some merit to this claim, right? That people are able to solve problems and they're using some of the other visual affordances to help them solve it, and they didn't really need the error message in that case. That was just sort of an extra that was there. So improving the message at the bottom would not have helped the developer in that case.
So what if we generated the fix for them?
Yeah, so the second paper talks a lot about this. So on this one, I'm mostly focusing on the comprehension side. But you'll see in like automated programming repair techniques like quick fix, there's more of a verification challenge there. So the developer wants to know what the fix is going to do to their code. They want to make sure it's going to do the thing it says and only that thing, and they need some way to verify what has changed between the two things. So So quick fix is sort of the inversion of the error message, right? One thing sort of tries to explain what the problem is, and the other tries to automatically repair or solve the problem. And I think one of the challenges, or one of the interesting challenges here, is making sure the two match up. So oftentimes in IDEs, quick fixes are actually orthogonal to the message, right? They give a very generic set of, here's some program repair strategies, but they're not necessarily conditioned on the error message. And that's one of the reasons I said people may get incorrect judgments, right? They may apply a quick fix. It removes the defect, but that wasn't what so it may remove a method or something, but that wasn't actually the problem in the code based on the message. It just incidentally happened to repair the program. So that's a good question. Okay, so this led us to our first research question. Do developers read error messages? Yeah. Okay.
So maybe this message would be useful to a person who is new to the language. Mm-hmm. And maybe depending upon whether you're targeting students who are learning their first programming language, or people who know some programming languages but they're programming in a new language, versus someone who are experts. So maybe it has also got to deal with who is the person or what background do the people have. when they decide whether they want to look at these messages or not?
Oh yeah, absolutely. So the reason we were able to solve it is we've written thousands and thousands of switch statements. So we already have a schema in our head. You could imagine even without the X, just by scanning, something seems odd, right? And you just say, oh, I'll fix the typo here. But for a novice who's first learning how do braces work, etc., they might need a much more verbose message. It might not say syntax error on default. They might say, okay, here's what switch statements are supposed to look like, etc. A lot more verbosity there. So that's true. For this study, when I get into methodology, you'll see our population, we consider them to be sort of entry level into industry programmers. That's who the subjects of this study was. But you're right, experts may do very different things than what I'm describing here. So our first research question is, do developers read error messages? And if they do, what can we learn from how they're reading? So let's return again to one of the tasks that we did before. So similar to the thing I did there, for the task, we do essentially the inversion. So we look at the study from Google, who provided a distribution of what they called costly error messages, messages that in their company were difficult to resolve for one reason or the other. Obviously, we didn't have the Google code base, but we used a comparable library of data structures from Apache Commons that has, reasonable data structures like lists and trees and things our participants would likely to be familiar with. And that way, we don't confound the task, them working with data structures, with the error. We used the Eclipse environment for our study. All of our students who are entering industry were familiar with this IDE, so that's what we used. And we made a minimal change to the syntax to inject default and tested it against the original error message. So here we would remove the colon, and this would be one of the costly syntax errors from the Google paper. And we did this for 10 different types of tasks for the top errors in their distribution.
Why is this a costly syntax error?
So the way they define costly is both in terms of frequency and the cost, the time to fix. So they used a metric that balanced both and called it costly. So in this case, the cost comes from probably the frequency, right? It happens all the time. For a novice, this might be a big problem. For an expert, it's more of a nuisance, but because it happens so often, it ends up being something that you'd want to prevent. So in your case, the example you gave with the quick fixes, right? So it's a costly error, maybe just alt-entering your way through this should fix it without them having to manually sit there and find the missing colon. So we had 56 participants recruited from undergrad and graduate courses. They had a mean of 1.4 years of professional experience, so this was paid positions, so that's why I consider them entry level. They self-rated themselves as having median knowledge about Java and familiarity with Eclipse, for what that's worth. And for this study, one reason I've picked it is we chose an interesting methodology of using eye tracking over other techniques. And the reason is that reading is primarily a automatic subconscious activity. So when you're looking around, you don't choose to say, I'm going to read that or not read that. It's just something that sort of happens as you're looking across the screen or looking around the room. And furthermore, it makes it unlikely that participants would be able to actively report what they were actually reading. So it's very hard to say, I'm reading this, I'm not reading this. And so we relied on this sort of passive measure to figure out what they were actually looking at on the screen. All right, so for the study design, we gave them 5 minutes per task. And we randomly assigned the task to mitigate learning effects. If the participant was totally perplexed after 2 minutes, they could just say, I give up, like, I'll never figure this out, and they could move on to the next task. To sort of help with reliability, we asked for a reasonable solution to the problem that they thought best captured the problem. So you can imagine deleting the project removes the compiler error. That's probably not the correct fix, though. So we asked for reasonable strategies. And we were specifically interested in how the tool or the IDE was affecting their ability to solve the problem. So we disallowed external resources because of that reason. And finally, we had a post-questionnaire and a calibration portion of the study, which we expected to take about an hour. So as they were completing their tasks, we also video captured their screen, as you can see here. And we performed some bunch of image recognition engineering to mark areas of interest. So for us, these are things like the little rectangle spaces here. So here's a problems pane, an explorer pane, an offline pane, etc. And we mark these through image analysis for all of the different frames in their project. So essentially, you can think of areas of interest as just rectangular regions of the screen that we wanted to be able to know when they were looking at. So for our analysis, we did the following. So for each frame in the video, we know what areas of interest are present. From the eye tracking data, we get a pixel location on what they're looking at on the screen, and we get something called a fixation, which is a sustained duration on that particular point. And if you combine the two, you can now say at a certain time, 15 seconds, they were looking at the problems pane to know what they're looking at throughout the IDE.
But then you will not be able to differentiate between where it says there's an error on this line, and then it gives a description of that error.
Yeah, so this is in our, so one of the limitations of this is the resolution at which we're able to identify. So we can't do word for word analysis, for example. We don't have that sort of resolution with the eye tracker, but we can, so we have to make some assumptions. So tooltips we can do reasonably, but we don't know what word they're looking at in the tooltip. We just say they're somewhere in the tooltip. Similarly, in the source code, we don't know what exactly what word they're reading in it, but we just say they're in the source code area for that. Same with the problems pane. One way we mitigated this was to make sure that there was only one error in the problems pane. So if they're looking inside there, we just say that's probably one they're looking at. That way we didn't have to differentiate, there's 6 errors, which of the 6? And we partially did that because of the limitations of the eye tracking.
So I'm curious if this is a new idea, or other people have tried this thing in the past, or what else have they used to study these kinds of things?
So when you say these kinds of things?
So maybe you can actually interview them and they can speak out their thoughts loudly about any activity that they are doing.
Yeah, so actually the sort of motivation for this was a pilot interview study where we asked people about experiences with errors. And we would get responses sometimes. It's, oh, I never read those error messages. They're just too weird. I try to figure out the problem myself. And if I'm not able to figure out the problem, then maybe I'll go back to the error. Unfortunately, there's a gap in the literature where we don't really know sort of how they're looking at things on the screen or if they're looking, and that's where this study came in. Other ways to do this is, so at Google, they instrumented some telemetry for one of their compilers. And what you would do there is you would just capture, so they have sort of a centralized version control system, and all their tooling is centralized. So it's collected in a single point. And what we did there is we added some telemetry to the compiler toolchain. And every time they got a compiler error, we could get metrics and we could see whether changes to the compiler errors were influencing their frequency over time, right? So if it's a very difficult error message, let's try to improve it. And then if we did a good job, we should see, faster resolutions of that error message, for example. So that's another way to do it. Other techniques I've used, not for this study, they're called like fly-on-the-wall experiments, where you observe people. You just sort of sit in a room and say, I'm going to stand in the corner and watch you work. And every time you see them, make some gesture of frustration, you look over and say, oh, what are you doing now? And sometimes that's necessary to sort of see ecological validity. I want to know real problems that are happening as they happen. One way to do fly-on-the-wall there is I've seen people instrument and then run really fast. That's the cost. So they get like a little text that says, oh, one of your participants has had this problem. If you do the study in the same building and you're on site, you can run down and look immediately. And that feedback is a lot more reliable than, say, retrospective, asking them what happened, an hour ago or whatever. So those are some of the other techniques. They all give you different things. The other techniques are very hard for them to say, what does reading mean? Probably all they can say is, yeah, I read it, but they won't be able to say, how long did I read it? How did I read it in proportion to the other things? That sort of thing. So that's what we were interested in here. Okay, so I'm going to speed up a little bit. So let's break this question down into 3 sub-questions. First, do they fixate on error messages? So is there a sustained duration? on any AOI element. How long do they spend? And to try to confirm, like, what does reading look like? Is that really reading? You could imagine they're just sort of staring at the screen or something, and that counts as a fixation. Okay, so a fixation, I said, is a sustained gaze on a particular location. Typically, we render them as sort of circles, and you can see the radius of the circle indicates sort of how long they're looking at that point. So here, we didn't really do word level analysis, but all of these fixations were in the sort of tooltip area, so we say they were looking at a tooltip error message here. And in our case, every participant, every task fixated on the error message at least once. So it's sort of like rejecting the null hypothesis. We can't say that they're reading yet precisely, but there is a fixation on every error message at some point during the task. So how long do they spend on the error messages? Well, for the source code editor, we see that 71% of their time is spent in the source code itself, but somewhat surprisingly, 20% of the task time is spent on error message information. So 20% on looking at the problems pane or the tooltip, trying to read or understand the message. And if we look at the mean and max times, you'll see just some variability around that. And the most common element that they used in our study is the problems pane. So they used the problems pane at the bottom of their screen when they're looking at error messages. And part of the reason we think this is it's always available, and tooltips sometimes occlude the code that they're trying to look at. So they constantly have to go back and forth to open and close the tooltip. Okay, so participants spent 13 to 25% of their time on error messages, and the problems pane was used more often, most often. So is that really reading? Because they could just be looking at the screen, doing some other activity. So here we did one last check, which is we used an existing study by Rayner that said mean fixation time is an indicator of reading. And so we looked at this in several ways. One is we compared it with a baseline of silent reading of just general English text. And the intuition here is that we expect that source code is probably more difficult to read than, say, like a James Patterson novel or something. And so if the source code was a lot easier to read than silent reading, it might indicate some sort of problem in our eye tracking study. And what we found is that reading source code is about, here you see 400 milliseconds, and reading error messages is actually marginally more difficult in terms of this mean fixation time metric than reading the source code. And we quantified this similarity through a measure called KL divergence, which is in the paper. But you can see that the error message and editor distributions are a lot closer than the silent reading. So based on all of those things, we concluded that participants were reading, that participants do read error messages, and that the difficulty of reading the error messages is comparable to reading source code. So perhaps reading error messages is still confusing for developers, but at the end of the day, it's just some sort of nuisance or frustration, like the problem with the default. They end up adding the colon and fixing it. So it didn't really influence their ability to make a correct judgment about the program. So the next thing we wanted to try to ask are, sorry. So the next thing we wanted to understand is, are the compiler errors difficult to resolve because of the error message? That is, can we attribute some complexity or confusion with the error message as influencing their ability to resolve the task? And that would connect the two pieces. So in order to do this, there's a couple things we need to know. First, we need to know if the resolutions are correct. So for each of the tasks, we went through against the unit test library to see whether they successfully or unsuccessfully resolved the defect. And we marked those tasks with either correct, incorrect, or they ran out of time, and we coded those differently. The second thing we need is some measure of reading difficulty. And sorry, the second thing we need is some measure of reading difficulty, and for that, we use this idea of revisits, with the intuition being that revisits, it's correlated with difficulty. So when someone leaves a particular area of interest and comes back to it, that count is a measure of difficulty for that region. So what we do with that is we construct a logistic regression with two axes. The first axis is a probability of correct solution and the number of revisits. And we see that there's a relationship between the number of revisits to the error message and their probability of getting the solution correctly. Unfortunately, this answer is a bit more nuanced than I would like. So are the compiler errors difficult to resolve because of the error messages they're getting? So on one hand, sort of yes, it is a significant predictor of correctness. Unfortunately, the R squared, one of the sort of percent variation explained is pretty low. It's 0.16. And the way you can interpret that is reading is just a proxy for other things. So like you were talking about, their familiarity with the code base, their expertise, all of these are actually the primary factors, and you're seeing that through their reading behavior. So it is a significant predictor, but it's just one of the many factors that are contributing to the difficulty of the task. Okay, so for time, I'm going to skip one of these. So in summary, participants spent between 13 to 25% of total task time on error message errors. The difficulty of reading error message source code is comparable to reading the difficulty of reading error messages is comparable to reading source code. And that may actually be an opportunity for improvement, because we would like error messages to be much simpler to read than the thing they're trying to fix. So there are some opportunities there. And the participant difficulty with reading an error message is a significant predictor of task correctness, although there are many other factors that also influence this. Okay, yes?
So after doing that study, what do you think is your role as a researcher? Right? Are you done with the recommendation, or do you feel that the group is also going to research on how to improve these error messages?
Yeah, so the next steps now are, what this study did is it essentially established a baseline, right? So we looked at existing tools. We didn't do any sort of manipulation. We said, okay, in Eclipse, what's the reading behavior that we're seeing? And now, using the baseline, we can say, okay, let's come up with what we'll call Eclipse Prime error messages, an improved set of error messages that either make them simpler to read, or maybe for novices are more explanatory. And now, comparing against the base set, we can see if there's an improvement. So we can say, okay, were the number of fixations reduced with the new error messages in contrast with the old error messages? And if they were, I skipped some of the slides, but if that's the metric we're using for difficulty, if that change has happened, then we can say, quantify the difference in difficulty and say the error message is now simpler because the number of revisits were reduced.
But I'm just curious logistically, right? So is the research group that conducted this study, which of course included you, so are you folks going to be following up on this in terms of how these error messages can be made better?
The answer is yes. I have a paper in submission that does that. We are investigating some theories for how to improve the error message, and one of them has been looking at this idea of argument structure. So when people want explanations of things, you can imagine an argument where they say, here's the problem, here's why it's a problem, etc. And we've been looking at framing compiler errors in terms of more of an argumentation style of structure, where it says, here's the problem, here's the evidence for the problem, to see if that sort of bootstraps people's processes to say, oh, well, I'm missing a default statement, here's the rationale for why that's a problem. Okay, now I understand what's going on, where previously some of the fixes we've seen point to a problem, but they don't necessarily indicate why that problem is a problem, which may account for that additional time. So that's in progress as sort of the tail end of my work on textual manipulations of how to present the error. Okay, so for this next study, I'm going to skip no intro, no methodology. I'm just going to focus on sort of one of our learnings, and this was related to the quick fixes that we were talking about before as one way of fixing a defect. So from the previous studies, we found that a particular feature of IDEs is quick fixes that are little automatic program repair tools that let you resolve the defect. And sometimes they use these to their own detriment. So they thought it would resolve the defect, but they actually didn't. So let me show you a quick example of how the quick fix works in existing tools. So the developer has three choices here for types of fixes, and in Eclipse you get a little sort of preview pane of what the code will change. So here they're trying to sort of figure out like what fix to apply, and they do. They select one, and now they're trying to see below what the fix actually did into their code, right? So that's the general mechanism of the quick fix as they work in tools today. So what are some of the problems we saw in the study? One is that quick fixes are fast, but they're prepackaged. So they're all or nothing in quick fixes and IDEs. So in that example, I either had to take one of the three fixes or do a lot of manual work to get the code into a state I wanted. And so one of our findings here was that it was important to have an opportunity to evaluate a space of fixes. So not only would they have had to manually apply a fix if one of the fixes didn't work for them, you saw that there were three possible choices there. And it was very hard to figure out, should I pick option A, option B, or option C, and what's the impact of those selections. You didn't see this in the video, but quick fixes sometimes are prepackaged options, so they may only partially support the developer's intention. So maybe one of the fixes was add all exceptions to the catch. And they actually wanted some to go in one place and some in the other, and the tooling doesn't really support that sort of nuance. So our goal with this sort of interaction was that just because there's a large design space of exploration doesn't mean that our options are we either provide tool support for the developer or no tool support. We can do something in the middle sometimes. And that's what our Eclipse slow fixes, called fix bugs, does. And the idea behind this is similar to before. They see an error message at the bottom of their screen. They're reading it. But instead of looking at the fixes, they go into this fix bugs mode. So this is the same catch exception defect. And now they're able to compare sort of what the suggestions are going to do side by side. And maybe they didn't like the default fix. And they're relying on the underlying sort of static analysis lexing of the system to give them drag and drop points for valid targets. Because we know that conditioned on the error, there's only certain places in the code that they would want to go. And this would minimize, you know, copy and paste problems and things that would happen if they were trying to do this manually. So the summary of this tool is it allows them to enables exploration of alternative design spaces. So you saw multiple quick fix options. You can easily see the differences between them and what it will do to your code. Second, we provide preview feedback, which is the mechanism through which they understand the different options. And when possible, we don't just give them tool support or no tool support. We provide a mixed initiative system where they're able to, when the error message allows for it, to do things like drag and drop, knowing that there are potential candidates in the space that are likely that they would want to do. Yes?
So this drag and drop works for exceptions, but what else can it work for?
So in the paper, we evaluated several types of error messages. So you can think of string formatting functions. So the example we were looking at earlier with date types, they can rearrange. So think of variable arguments and string formatting. If they change the argument, they can drag and drop that, and the corresponding string argument can change also. So what are some other manipulations? So those are the two. So in switch statements, for example, if you want to move cases around, yeah, you can copy and paste the case, but really, like with block structures, probably you want to rearrange the whole case statement. You don't want to take just this logic and not the other. So, so any of those sort of block situations where you want to manipulate block structures at once are good opportunities for this sort of drag and drop interaction. One of the downsides of it is they work really well in local contexts. So if the drag and drop actions you want to do are within the same file, those work really well. There's a sort of a penalty when they're far apart, right? Like, how do you drag and drop when the thing you want to drag is all the way at the top of the screen and your code is at the bottom? So there are some limitations there. But
and do you think it's kind of useful gesture even while doing the coding exercise as opposed to fixing it after compiler shows some errors?
Yeah. So this is actually something you could use even without the compiler error. So if I'm opening a file, I know there's different types of exceptions. So in Java, there's IO exception, etc. And at that point in time, the drag and drop, if that affordance was available, it's useful to say, oh, well, I added the drag and drop by default because most people want it in the catch block. But if you want it in the throw, we should make it, you could use drag and drop to do that as well. So, yeah.
As you have added these more complex affordances, have you given any thought to accessibility? How to get the whole set of customers?
Yeah, so one of the first time I presented this study, one of the things that came out of it was there are a lot of users that are keyboard users, right? And like for either they don't want to use the mouse or they're unable to use the mouse. How would they take advantage of these drag and drop systems? So one of the things we've been looking at are some tools have this, like Sublime Text. They're called jump points. So what you do is when you want to do a drag and drop operation, it labels each of the points on the screen. So you can say, okay, I want to do some key combination to enable drag and drop. And now every drag and drop element has a label next to it, like a letter. And you say, okay, for source, I want B, and the target is Q. And we haven't evaluated it, but we think that both individuals who don't prefer to use the mouse and those who can't would find that to be a satisfactory way of doing these sort of drag and drops without having to actually do them with the mouse. So, okay, how are we doing on time? Good. So the final study I want to look at was conducted here at Microsoft Research. In the last two studies that I showed you, we looked at, way back, if you remember, I talked about computer-initiated explanations to the user. So these were tools that were giving you feedback, such as when you had a compiler error or some form of error. And in this study, I'm really interested in this idea of user-initiated explanations, where the computer, there's nothing really wrong per se, but the user wants an explanation or wants an answer to some form of system. So this was a study I did at MSR in 2015. I guess Rob's in the room and Steve's in the room, so a lot of the authors are in the room to correct me in case I say something wrong. So again, so we were looking at the flip side of the coin. So we said originally we started the study looking at developers. That's where we thought this would go. So developers, they get bugs in their code statically with compiler errors, etc. But we found that developers were also looking at log files, so maybe there were some opportunities for tools to help developers work with log sort of telemetry data to understand defects or issues in their code, such as with performance. So this is, at least what we thought, this is a very familiar story to us. When software developers talk about log data, what comes to mind is it's the output of some sort of timestamp trace statements in the code. So they'll say, oh, it's basically just print statements. And so our expectation was that a software developer who looks at log files might use this to troubleshoot the bug. And maybe they're using tools like Notepad++ to highlight lines of code, to filter, to search for the root cause of the defect. So when I came into MSR, I thought, oh, well, maybe we'll be able to build some better tools for developers, that are better than Notepad++ to help them out, just like we were doing with the compilers. So what I found, though, when we came here is that as companies were shifting more towards the service model, we thought the landscape would change a little bit. So it's not just developers working with local log files on their disk, but they're now looking at other forms of logs, which we call telemetry or streaming data, right? As a result of things that they're deploying in Azure or other places, and they want to be able to understand the sort of data in rest and data in motion. So again, like I said, when we began the study, we thought, let's set out to look at developers to understand how this sort of data-driven shift in understanding customer behavior, fixing bugs, has introduced new challenges to them, which might mean that they need new tools to help them above and beyond what Notepad++ can offer. But to our surprise, Rob and I discovered very early on that the availability of event data isn't something that was just affecting developers. It was being used all across the organization at Microsoft, and it was being adapted for a variety and range of activities beyond the traditional software developer. And so when we saw that, we wanted to ask, so how are different team roles using event data, and what are they doing with this? What are business managers, et cetera, doing with event data? And then the original research question again, what are the challenges that people are facing when they're working with this sort of event data? So again, we used a different style of study than the first two. Here we did a mixed method study where we conducted 20 semi-structured interviews from a variety of different roles in the Redmond area. And we intentionally, based on that early finding, included both technical and non-technical roles to see what types of tasks they were performing with log data and event data, et cetera. Within this interview format, we used a storytelling format. So we asked them to share experiences of a time when they've used event data in the recent past, and what are the challenges they were facing with this. So this is sometimes called the war stories format because it's a big pain point I had recently with a particular problem. And finally, we then qualitatively coded these challenges and the activities to construct sort of a list of activities and challenges. Okay, so those are just interview studies. What we wanted to do from that is we wanted to confirm whether the interview responses generalized across the company. You know, if this was a problem just for these 28 people, or if this was a problem across the organization. So we turned those activities and those challenges into survey questions, which we sent out to about 1,800 responses from all of the locations as at Microsoft worldwide, and we presented the challenges as statements. For example, the tools for this activity aren't easy to use, and they got to mark whether they agreed or disagreed with that statement.
So what tools are you talking about here?
So we didn't focus for the survey on a particular, so any sort of data analysis tool, which could include Excel, R, Power BI. We just wanted a sense of when you work with event data, what are the challenges that you face? And in the paper, we see, data scientists seem to use R and do a lot more scripting. Managers tend to use more Excel, Power BI sorts of tools. Some teams in the organization have built a lot of their own custom tooling to do reporting. So we interviewed people, for example, in Windows updates and operating systems groups, and they have a lot of custom dashboards that they've built and infrastructure to help them understand, ask questions about their data and give answers to it. But for the survey itself, we were just interested in anyone who works with data. What are the problems that you see in your job role? What are the problems you see in your job role? Okay, so here are the results. So for RQ1, which was how are different team roles using event data and for what work activities, we identified 8 different work activities that were happening within the company. And we've ordered the distance here from sort of the level of where they are from the raw data to sort of looking at high-level reports. So engineering the data pipeline, they do what's called sort of taking uncooked data or raw data streams and converting them to cooked data for upstream consumers to be able to use. So there's 2 in particular that, since Rob, you're in the room, that we thought were kind of interesting. So one of them is this sort of vague activity called doing data science. And when we described this activity, we said, like, in the paper, can we really put doing data science as an activity? Because it's sort of so vague in general. But it turns out this is how our participants described it. When we asked them, what are you working on? They didn't say we're engineering the data pipeline, for example. They were sort of vague. They said, I do data science. And what this sort of reflects is that there's this very large spectrum in data science of the types of activities that people are doing. When you ask someone, what is data science? They don't have it's not a single answer. Like when I troubleshoot as a developer, I fix bugs, et cetera. There's this huge spectrum of activity. The other one we thought that was interesting, or I thought it was interesting, was improving the user experience. So unlike traditional user studies, we were finding a lot of UX groups at Microsoft using telemetry data to understand behavior at scale. Using data, right. So using telemetry data to understand data at scale, or understand behavior at scale, which necessitated for them tools to sort of understand what users were doing. Okay, so to continue this investigation, we looked at the activities in which different professionals use data at least once a week. So I'm just going to pick out one of these roles. So this is content publishing. So these are the people who make, for example, MSDN documentation for developers outside of Microsoft. And what we can see is we asked them, do you use event data at least once a week? And for what activity? And so for their primary activity, makes sense, they said we use content data for user experience, the telemetry. And as their second activity, they marked triaging bugs is what they use it for. Okay, so the conclusion of this is that it's not just software developers in the company, it's diverse roles that are trying to ask questions of data, and they're using event data to get answers to those questions. So you can see a range from program managers to content publishers to sales and services leadership, all trying to use tools and data to get answers to questions, whether it's about bug fixing or about marketing decisions, that sort of thing. The other thing that we thought was interesting that you don't see is that event data doesn't seem to be specialized. So there's not just one group that overwhelmingly wants to ask questions about data all of the time. Across roles, you see that 20% to a quarter of respondents use event data in their activity. And so what we learned from this is, for many individuals, asking questions about data is not a specialized role. It's just an occasional activity. So every now and then, I want to be able to ask a question about some data. And so that suggests that we want to build tools that are not necessarily specialized tools, but tools that people can sort of pick up and just use right away without a lot of onboarding to ask questions about their data. Okay, so there's a table in the paper that has a detailed breakdown of all the challenges for the larger community and for Microsoft. And what I've done here is just taken some of the common challenges that we saw across the different activities that people were facing. One of them was that combining multiple sources of data is difficult. Data doesn't come nicely prepackaged in a single spreadsheet or a single file. There are often files here, some are in databases there, and in order to ask a question about their data, the first barrier they often face is, how do I get all the data in one place to ask the question in the first place? And unfortunately, if the barrier is large enough, as we interviewed people, they would say, well, I wanted to ask this question, but since I would have to figure out how to do all this data source stuff, I just decided it would take too much time or too much effort. So they never actually asked the question that they would have otherwise asked had they had the tool. The last point I'll talk about a little bit more, they said the activity requires more effort than I have time for. And what they didn't mean here is that, a SQL query runs slowly. That's not what they were talking about. What they were saying here is that it's not their full-time job to ask questions about data. This is an occasional activity that they do. So if they want to learn something about data, it's something that they sort of have to interleave against all of their existing tasks or do as in addition to their normal job responsibilities.
Even for data scientists?
So there are data scientist teams at Microsoft that are formally data scientists. And yeah, for them, they do data science full-time. But even there, they said the activity requires more effort than I have time for. And the reason is slightly different. If you think of a decentralized model versus like a central hub model, what was happening with them is they were incredibly overwhelmed. A lot of different organizational units would always come to the data science team and say, can you answer this query for me? Can you answer this query for me? And they would tell us that, program managers didn't really understand. They think a question was very simple to ask, and they didn't understand the amount of sort of engineering effort that they needed to be able to answer those questions. And so even when they were full-time for them, they said, we're completely overwhelmed with just questions. And it's very frustrating at times because they're often very simple questions, like how many people ran Windows updates last week? And so when we talked to them, they were very encouraging of saying, we want to democratize this data science. Like, yeah, it's our full-time job, but for these simpler questions, can we sort of outsource them and give tools to other people to enable them to ask questions by themselves? And they told us that as data scientists, they wanted to serve more as maybe a consulting role. Like, we will work on the really hard problems, like credit card fraud, Xbox sort of performance issues, that sort of thing, that aren't simple queries. But in order to be able to answer those harder questions, they really needed to be able to offload these sort of simpler queries and let the different teams ask those questions without them. So the main reason, so one of the reasons we conducted this study is that different groups at Microsoft were aware that there were these data science challenges, and they wanted to come up with tools and interfaces to help all of these different groups. And where Rob and I came in for the internship is a lot of the justification for these tools came from things like informal interviews with groups. So they would talk to a small group and say, oh yeah, I have a lot of trouble combining data. And so we'd say, oh, well, let's build a tool that helps them combine data. And what we wanted to do at MSR during my internship is say, let's provide a solid empirical justification for the need for these sort of tools. Because if we can say across the company, combining data was a difficult problem, across the company, understanding and having confidence in the output of the data was a difficult problem, then it makes it much easier to develop and sell these sort of tools to different business units and provide justification for building them. So in summary, we thought developers were the only people doing sort of data science and maybe the specialized data scientist roles, but event data activities spanned across activities within the company. For tool designers who are building tools, it seems that, at least today, event data is an occasional activity that they do that's mixed in with other responsibilities. So the tools you provide can't be high overhead. It can't be something that when they want to pick up and ask the question, it's going to take them a long time to figure out how the tool worked, relearn it, and ask their questions. They have to be very lightweight. Finally, what we found at Microsoft is there's a bottleneck of having too few experts. And so even the data scientists here are telling us that there's this need to democratize data scientists, give non-technical team members ways to ask questions about their data. Okay, so finally, I'm just going to wrap up with some directions in different areas, and hopefully maybe one or all of them will resonate with you. So the first direction I've been thinking about came with conversations at eCoop that I had with some members of the programming language theory community. So these are the people who come up with proofs, do program synthesis, model checking, they use rule-based static analysis, and they have some very sophisticated technologies and techniques for making sure that programs are correct, that they're sound, that they're doing what they're supposed to. But one of the immense sort of frustrations they relayed to me is that people don't use these tools. They can't understand the output of them. So one of the directions I'm thinking about looking at here is how do we get from theorems to human-friendly explanations? How do we get from, say, output of model checking, where typically it gives examples or instances of the problem, to presentations of the output of these theorems in a way that humans can understand? So we saw one of them in the fix bugs, where we said, okay, the static analysis tool already knows possible drag and drop targets. How do we present that information to the developer in a way that they can use the output of that analysis? So the work that Sumit and the pros group are doing, for example, in FlashProg, it's using program synthesis. We can't expect end users to know program synthesis, but we want them to be able to leverage all the sophisticated techniques that are available in that domain. So how do we come up with interactions that map the theories together in a way that people who are not formal methods people can start using them and interacting with them? So the third one is, another idea in this direction is with error messages. So Krishnamurthy has been looking at, often for proofs in PL, they'll do what's called desugaring. So they take the language and they canonicalize it to some reduced form. So the simplest way you can think about this is if you have for loops and while loops and do loops, you may just reduce it all to loops for purposes of the analysis. But now in order to give feedback to the user, you want to give feedback in the same domain that they were working in, not the reduced language. So there are techniques like resugaring, which say after analysis, how do you trace back to the original way in which the developer was actually writing the code and present the information that way, rather than in the domain of the algorithm or the theorem. Okay, so the second direction that we've been looking at is, or that I've been thinking about, is programming tools are a nice opportunity to apply some of these formal methods and techniques, and that's a great starting point. But what I'm seeing is that there's opportunities to help many other types of tools, not just software engineers. So the example I gave here is this is some work Emerson Murphy Hill and I did on ambient visualizations for code smells. So here it would show a little pedal, and maybe the pedals represent long methods or other problems in the code. And what we looked at is, can we apply some of those same programming language techniques to other domains? So we said, well, the pedal idea might also work for people who are writers. It could be a grammar checker as people are writing code, or writing English paragraphs. And so we used the technique of the code smell static analysis and applied it to grammar checking for, here it's redundant phrases, where it points out redundant phrases in your paragraphs that you can then select which of the phrases you want. So you can imagine this sort of technique also being used maybe in log files or telemetry. So there's log files over there, and the pedals each represent different types of anomalies it's finding. Maybe some of the pedals represent lots of repetitions, another pedal represents extreme values in the code, and so on. So thinking about ways to take classical PL techniques and make them for other types of domains that we don't normally think of as being programming. So the third one, and my third and final one, came from some research. Actually, I started doing this with Tom on gamification and making software and engineering environments more playful and play-like. And in this particular slide, let's not think about play as fun or video games, but sort of play as tinkering or spontaneity, sort of lightweight sort of analysis that people would want to do in their systems. In contrast with environments like Visual Studio, I think one of the opportunities for user-initiated questions are to think about our tool design in terms of play. So some of the metaphors here are play as tinkering. Does it make it easy to tinker with the environment that you're in, or is that a very difficult process? Play as catalyst means people who just want to explore data or some sort of question as a starting point, and if they need to, they want to start programming, right? But they don't want to program unless they absolutely have to. And so now, using this sort of play as a metaphor, we can evaluate tools to say, does this support play as a catalyst, or does it force them to program and write difficult scripts right up front? Similarly, we can think of play as spontaneity. So people just sort of get together and play, right? People usually don't say, I'm going to have fun today between 4 and 5. That's the only time I'm going to have fun. So if we think of that in terms of tools, we can say, is it easy to just bring up the tool, ask the question that you want, and then put it away? Or do you have to allocate these sort of pre-planned big sessions in order to be able to use the tool? And through the play metaphor, our preference would be that we want to build tools and evaluate them such that we can quickly load them whenever we want, ask our question, and then put them away and continue doing our task. Okay, so to wrap up, in conclusion, developers spend significant amounts of task time comprehending and resolving error messages. Here, looking at the PL to explanations and some of our previous work, it's important to appropriately surface information internal to the compiler and not just expose it, but provide it in a way that is aligned with human presentation to make it human-friendly. The second conclusion is that the role of software developers are changing in many ways. They're not the folks we think of as using an IDE, using Visual Studio all the time, or Eclipse, or a professional development environment. We see more end-user programmers who don't necessarily have formal programming experience, but they have a need to perform program activities, sometimes spontaneously, And sometimes they may not even realize they're programming, but they actually are, or they should be. So they may be doing a task manually, like copying or renaming files, in which case there is an opportunity to help them with the tool. They just don't realize that it's there. And if that's true, then that means that approaches that are traditionally designed for programming environments can potentially find applications in non-programming domains, as we saw with the adapting the IDE to the writing environment using many of the same affordances and tools. So thanks. That's the end of my talk. Yes.
I really like your presentation. It's awesome. You mentioned formal programming experiences, and you mentioned that most current programmers or developers, they don't really have formal programming experience. Can you elaborate a little bit on that? Like, what is a formal programming experience?
So typically when we think of software developers, we say that they've had some sort of background, either an undergrad degree or they've had some computer science experience with algorithms or data structures or a course in programming languages of some form, right? When I talk about these sort of end-user programmers or informal programmers, you can imagine someone who learns programming in an ad hoc way. So they start using Excel, right? And at first when they use Excel, they just type stuff into the computer. They type a list. And then one day they discover the sum feature, right? And so they say, oh, I don't have to manually add these columns. I learned the sum tool, and they select it and hit sum, right? And then maybe later they pick up an if. They see, oh, well, sometimes I want the color to be red, sometimes I want it to be green. So they're not formal programmers in the sense of I had a well-defined curriculum for how to program. I learned how to program in school or academically, but they're still doing programming sorts of tasks, even though they may not themselves call it programming. And we're seeing sort of a need to support that community as well as they're doing more and more sophisticated tasks. So right now, maybe they're doing some, but we see chemists who are doing fairly complicated formulas within their spreadsheets. We see individuals who are using tools like Tableau, where they start out using the graphical interface to do designs for the questions they want to ask, and sort of ad hoc, they drill down into the query and they start by making small tweaks initially, like, oh, I need to change a less than to a greater than. I forget where this is in the GUI, but I'm going to go drop into the source mode, and I probably figure out myself that this true should be false, or this less than should be greater than, etc. And so this is sort of a very different style of programming than we think of in terms of IDE, where people are building projects, thinking about, how should I architect my model? Where should I put my views? It's very ad hoc, sort of as needed programming that they're doing to get an answer or solve a task. It may not even be reusable. They may just ask the question once and then they delete the spreadsheet when they get their answer. So. Okay.
One of the problems I'm seeing a lot of is the occasional use of these tools.
Mm-hmm.
And you highlighted that a
Yeah.
little bit before. And can you elaborate a little bit more on that?
Yeah, so one of the challenges with tools that people use occasionally is they don't sort of build the familiarity or the muscle memory that they need to perform the task. So an example of this is, I know how to do a t-test, like as part of my PhD program, but every time I load up R, I can never remember what library I'm supposed to import to call it, what the format of the arguments are, how I'm supposed to use it. And so oftentimes I will just not use R. In contrast, there's a tool called Jump, made by SAS, where I don't have to think about those sort of details. I can just say import a spreadsheet, analysis. It has the 3 or 4 most common analyses that I might run. It doesn't have the full set that R has, but it doesn't matter. I do very basic things in it. And then I run the t-test through a GUI. And this is something that even if I completely forget Jump each time, I can rediscover the functionality every time I open it within a few minutes. I can say, oh, it's probably under analysis. It's probably under statistics. There's my t-test. Whereas with R, if I'm not doing this as an activity full time, there's no way to discover how to do a t-test other than look at the help documentation, relearn, look at the R book, etc. And so if we want to support this occasional usage, we need to do a couple of things. One is we need to figure out what tasks people most frequently do as part of their occasional usage, rather than trying to support all of the possible tasks anyone could possibly do. And the second thing is we need to think about interfaces that are sort of self-discoverable. We can't expect people each time to open the manual in order to perform a simple operation. So those are my thoughts on the design there. Some more playful designs I found thinking in terms of like play as a metaphor has helped me build the occasional activity style of tools. Yes.
I wonder if you're familiar with some recent work in the space of giving feedback to students on introductory programming assignments. So especially with the advent of MOOCs, the interaction between the teacher and student is much further reduced, and there's increasing interest in seeing how we can do automated feedback generation for students. So I wonder if the study that you described in the first part of your talk around this IDEs tracking to figure out the challenges that developers are facing in fixing errors can be adapted to this setting of understanding where do students actually struggle with when they are trying to learn programming, and how would you adapt your study to this setting?
Yeah, absolutely. So it's kind of creepy, but there's some recent work on using webcams as eye trackers. So if you choose to activate it, there's some Chi papers on using conventional web cameras on your laptops to sort of look at you and then triangulate with what you're looking at on the screen. This would help in non-lab environments like MOOCs where people are working at home or wherever else, instead of having to have a professional eye tracking setup. You could use that to figure out what they're looking at on the screen. In terms of, there are some differences and similarities between the two works in terms of error explanation, in terms of the goal. So typically in a MOOC, we think about like hint systems, because we want them to actually learn how to solve the problem in the end, right? So it's not just about providing feedback. We want to make sure that once the feedback is removed, that they conceptually understand the problem, that they're not relying just on the feedback in order to solve the problem. Whereas in the professional developer space, it's more like the pulley, right? The goal there isn't one day you'll be strong enough and we'll remove the pulley per se. This is just another tool in your toolbox, and you just get to use this on and on to solve your daily development tasks. So I think there is some overlap there, but the end goal is a bit different. One is sort of feedback for learning, which you might intentionally actually give less complete feedback in that case, right? You don't want to give them the answer right away. So you might say, or you might give them fuzzy feedback. So one of these 5 lines in your program is wrong in your switch statement. Which one is wrong? You could imagine that you would never give a professional developer that in their tool and say, one of these 5 lines is wrong, because they just tell me which line is wrong. That's what I want to fix. So that's a really interesting space, actually, in terms of also how to onboard developers to tools. What should you do? So someone starts out coming in. Visual Studio is a very complicated IDE. Are there sort of levels of progressive disclosure where you can get novices to start using tools and progressively onboard to the more complicated functionality in the IDE? I don't know if that was a full answer for your question, but there's definitely overlap in the two spaces. So.
Kind of interesting when you're talking about these progressive UIs. I think about some applications these days have UIs that adapt to the user.
Mm-hmm.
Certain things hide, certain things appear. And do you know anything about the success of those, and particularly this case of how does that intersect with occasional users? You know, on the one hand, if I'm an occasional user and I always use one feature of the tool, it's great if that's the only thing that's visible on the menu. On the other hand, every time I come back, it's different. It drives me crazy.
You may remember the customized ribbon, the menu study. I don't remember.
Really problematic.
So there's a tension between exposing just the functionality people use versus muscle memory, right? So one of the big problems is like even Word 95. I still remember it was like tool spell check. You just do this. There's the spell check. But if that moves, right, like you've taken basically implicit knowledge that you've built into your sort of brain somehow, and you're basically forcing them to relearn an interface every time. Adaptation is particularly tricky because if the person who's using the tool doesn't have agency or control over the way it's adapting, it can change on them when they don't want it to change. They may want it to change and not have the ability to get it to change. So they may say, I never use this feature, remove it from the menu. But if the only way to remove it is to not use it, then that's sort of a source of frustration. So I think progressive complexity is important, but based on the research I've seen so far, automated complexity management, either because it isn't at the state it needs to be or because it's not a good idea, hasn't seemed to have worked very well, at least based on the results I've seen so far.
Send this video again.